In single-variable calculus, the difference quotient is usually the name for the expression which, taken to the limit when h approaches 0, gives the derivative of the function f. The name of the expression stems from the fact that it is the quotient of the difference of values of the function by the difference of the corresponding values of its argument x equals h. In this case, the difference quotient is a measure of the average rate of change of the function over an interval. The limit of the difference quotient is thus the instantaneous rate of change. By a slight change in notation, for an interval a, b, the difference quotient is called the mean value of the derivative of f over the interval a, b. This name is justified by the mean value theorem, which states that for a differentiable function f, its derivative f reaches its mean value at some point in the interval. Geometrically, this difference quotient measures the slope of the secant line passing through the points with coordinates, and the difference quotient is sometimes also called the Newton quotient. Difference quotients are used as approximations in numerical differentiation, but they have also been subject of criticism in this application. The typical notion of the difference quotient discussed above is a particular case of a more general concept. The primary vehicle of calculus and other higher mathematics is the function. Its input value is its argument, usually a point expressible on a graph. The difference between 2 points, themselves, is known as their delta, as is the difference in their function result, the particular notation being determined by the direction of formation. Forward difference. Delta f equals f minus f. Central difference. Delta f equals f minus f. Backward difference. F equals f minus f. The general preference is the forward orientation, as f is the base, to which differences are added to it. Furthermore, if delta p is finite, then delta f is known as a finite difference, with specific denotations of dp and df. If delta p is infinitesimal, then delta f is known as an infinitesimal difference, with specific denotations of dp and df as y. The function difference divided by the point difference is known as the difference quotient. If delta p is infinitesimal, then the difference quotient is a derivative, otherwise it is a divided difference. Defining the point range. Regardless if delta p is infinitesimal or finite, there is a point range, where the boundaries are p plus or minus delta p, delta f or f. Pound equals lower boundary, ub equals upper boundary. Derivatives can be regarded as functions themselves, harboring their own derivatives. Thus each function is home to sequential degrees of derivation, or differentiation. This property can be generalized to all difference quotients. As this sequencing requires a corresponding boundary splintering, it is practical to break up the point range into smaller, equi-sized sections, with each section being marked by an intermediary point, where pound equals p0 and ub equals pn, the nth point, equaling the degree, order. Pound equals p0 equals p0 plus 0 delta 1 p equals pn minus delta 1 p. P1 equals p0 plus 1 delta 1 p equals pn minus delta 1 p. P2 equals p0 plus 2 delta 1 p equals pn minus delta 1 p. P3 equals p0 plus 3 delta 1 p equals pn minus delta 1 p. Pn3 equals p0 plus delta 1 p equals pn minus 3 delta 1 p. Pn2 equals p0 plus delta 1 p equals pn minus 2 delta 1 p. Pn1 equals p0 plus delta 1 p equals pn minus 1 delta 1 p. Ub equals pn0 equals p0 plus delta 1 p equals pn minus 0 delta 1 p equals pn. Delta p equals delta 1 p equals p1 minus p0 equals p2 minus p1 equals p3 minus p2 equals pn minus pn1. Delta b equals ub minus pound equals pn minus p0 equals delta np equals n delta 1p. The primary difference quotient equals Pn. The Leibniz notation and derivative expressions do not distinguish p to p0 or Pn. There are other derivative notations, but these are the most recognized, standard designations. As a divided difference, however, does require further elucidation, as it equals the average derivative between and including pound and ub. In this interpretation, par represents a function extracted, average value of p. The particular valuation depending on the function averaging it is extracted from. More formally, par is found in the mean value theorem of calculus, which says, for any function that is continuous on pound ub and differentiable on there exists some par in the interval such that the secant joining the endpoints of the interval pound ub is parallel to the tangent at par. Essentially, par denotes some value of p between pound and ub, hence, which links the mean value result with the divided difference. As there is, by its very definition, a tangible difference between pound p0 and ub pn. The Leibniz and derivative expressions do require divarication of the function argument. Higher-order difference quotients, second-order, third-order, nth-order applying the divided difference. The quintessential application of the divided difference is in the presentation of the definite integral, which is nothing more than a finite difference. Given that the mean value derivative expression form provides all of the same information as the classical integral notation, the mean value form may be the preferable expression, such as in writing venues that only support, except standard ASCII text, or in cases that only require the average derivative. This is especially true for definite integrals that technically have 0 and either/or as boundaries, with the same divided difference found as that with boundaries of 0 in. This also becomes particularly useful when dealing with iterated and multiple integrals.